Welcome. Take a moment to settle in, without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered, or understood, or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight we are going to talk about the stars, slowly, without hurrying. Long before anyone thought to ask what the sun was made of, people were watching it carefully because its movements governed planting, harvest, festival, and calendar. Court astronomers in China kept written notes of dark patches seen on the solar disk when dust storms or low haze dimmed it enough to look at directly, and those observations were entered into the dynastic histories alongside comets, eclipses, and unusual weather, the oldest securely dated of them falling in the 1st century before the Common Era. To the observers who made them, the marks were omens to be recorded rather than features of a physical body, and the notion that a blemish could exist on the sun at all sat uneasily with much of what was believed about the heavens elsewhere. Among the Greek philosophers, Anaxagoras proposed that the sun was not a deity but a mass of burning stone, larger than the Peloponnese, and later writers report that this opinion brought him into serious trouble. A more mathematical attempt came from Aristarchus of Samos, who reasoned that when the moon appears exactly half lit, the Earth, moon, and sun form a right angle so that measuring the remaining angle would give the ratio of the two distances. His result, that the sun lay about 19 times farther off than the moon, fell short of the true ratio by a factor of roughly 20 because the angle in question is far too close to a right angle for naked eye work. The geometry itself was sound, and it carried a conclusion he was willing to state plainly: the sun must be considerably larger than the Earth. Eclipses gave a second line of evidence, and a much older one. Babylonian scribes had accumulated enough records of lunar eclipses to recognize the repeating interval of about 18 years and 11 days, which allowed a rough prediction of when the pattern would return, and Chinese and later Islamic astronomers built similar tables. During a total solar eclipse, the covered disk reveals a pale halo of light extending well beyond it, along with pink flames rising from the edge, and these appearances were noted for centuries before anyone could say what they were. That the moon fits over the sun so nearly exactly is a coincidence of the present epoch, the smaller body being some 400 times nearer and about 400 times smaller. Telescopes changed the question from what the sun signified to what it looked like. In the years around 1610 and 1611, several observers in different countries turned the new instrument towards it. Among them, Thomas Harriot in England, Johannes Fabricius in Frisia, Christoph Scheiner in Bavaria, and Galileo in Italy, and each recorded dark spots that drifted across the disk. A dispute followed over whether the spots were small dark bodies orbiting nearby or features of the sun itself, and the decisive detail was their shape. Spots appeared foreshortened into thin slivers as they approached the edge, exactly as markings on a rotating sphere would, and they took roughly a fortnight to cross from one limb to the other, implying a rotation period of about a month. Systematic counting came much later. Heinrich Schwabe, watching for a possible planet inside Mercury's orbit, kept daily tallies of spots for years and noticed instead that their number rose and fell. in a cycle of roughly a decade, a result he announced in the 1840s and which Rudolf Wolff then extended backwards through the older records. Richard Carrington, timing the drift of spots at different latitudes, found that the equator completes a turn in about 25 days, while regions nearer the poles lag behind, so the surface does not rotate as a solid body would. Carrington also witnessed, in 1859, a brief white flare over a spot group, followed within a day by severe disturbances of compass needles and telegraph lines. Measuring the distance took longer than measuring almost anything else in the solar system. A Mars parallax attempted from Paris and from Cayenne in the 1670s gave a figure of the right general order, and Edmund Halley then proposed a more precise method, using the transits of Venus across the solar disk, timed from widely separated stations, though he knew he would not live to see the transits in question. Expeditions were sent out for the pairs of transits in the 1760s and again in the 1870s and 1880s, and the timings proved harder than expected because of a smearing at the moment of contact that observers called the black drop. Radar echoes bounced off Venus in the 1960s finally settled the matter, giving a mean distance close to 149.6 million kilometers, which sunlight crosses in about 8 minutes and 20 seconds. With the distance known, everything else about the sun's bulk followed from simple measurement. Its disk spans about half a degree, which at that remove corresponds to a diameter near 1,400,000 kilometers, or 109 times the width of the Earth. Newton's law of gravitation, applied to the Earth's orbital period, yields a mass around 330,000 times our own planet's, and dividing that mass by that volume gives a mean density only about 1 4/10 times the density of water, which tells against any picture of the sun as a solid or molten globe of rock. Heat proved harder to pin down than size. Joseph Stephan, working from experimental results in 1879, proposed that the energy radiated by a hot body rises with the fourth power of its temperature, and Ludwig Boltzmann derived the same relation from thermodynamics a few years afterwards, which allowed the sun's surface temperature to be inferred from the amount of heat arriving at the top of the atmosphere. Wilhelm Wien's later work on the wavelength at which a hot body radiates most strongly gave a second and independent route to the answer. Both approaches converge on an effective temperature near 5,800 degrees on the absolute scale, a little under 5,500 degrees Celsius, while the core, as later calculations of pressure and equilibrium showed, must be nearer 15 million. Sunlight passed through a prism carries dark gaps at particular wavelengths, and once those gaps were matched against the bright lines emitted by heated substances in the laboratory, the sun's outer layers could be inventoried without anyone going near them. During a total eclipse in 1868, observers examining the spectrum of the prominences found a yellow line that matched nothing then known on Earth, and the element responsible was named helium, after the Greek word for the Sunday. It was isolated from a terrestrial mineral some 27 years afterwards, confirming that the chemistry of the sun and the chemistry of the ground beneath the observatory were the same chemistry. Whether the sun belonged to the same family as the stars was a question that could be attacked by brightness alone. Christian Huygens compared the light of Sirius with sunlight admitted through a tiny aperture and concluded that if the two bodies were intrinsically alike, Sirius must lie many thousands of times farther away than the Sunday. Newton reached a comparable conclusion by a different route, using the light Saturn reflects as an intermediate standard. Both estimates rested on an assumption they could not test, and it was only when Bessel and his contemporaries succeeded in measuring stellar parallaxes in the 1830s that the assumption acquired independent support. What kept the sun shining remained unresolved for most of the 19th century. Ordinary burning would exhaust a body of that mass in a few thousand years, and the best physical alternative, slow gravitational contraction converting potential energy into heat, gave an age of some tens of millions of years, which geologists and naturalists judged far too brief for the record in the rocks. Francis Aston's precise measurements of atomic masses showed that 4 hydrogen nuclei weigh slightly more than 1 helium nucleus, and Arthur Eddington argued in 1920 that the difference, released as energy, could sustain a star for billions of years. Hans Bethe and Carl Friedrich von Weizsäcker worked out the specific nuclear reactions towards the end of the 1930s. Direct evidence of those reactions arrived from a tank of cleaning fluid placed deep in a South Dakota gold mine, where Raymond Davis and his colleagues counted the rare argon atoms produced when solar neutrinos struck chlorine. The counts came in persistently below prediction, and the discrepancy was resolved only decades later, when detectors in Canada and Japan established that neutrinos change type in transit. Alongside this, the discovery that the solar surface oscillates with a characteristic period near 5 minutes opened a way of sounding the interior with its own sound waves, and the resulting model of a middle-aged star of moderate mass, warmer and heavier than most of its neighbors, but unremarkable among stars in general, has held up well. Sky records begin with the practical business of keeping a calendar. Farmers in Mesopotamia needed to know when to sow and when to expect the rivers to rise, and priests needed to know when a month should be intercalated to keep the lunar year in step with the seasons. So the risings and settings of bright stars were noted on clay in wedge-shaped script and copied from generation to generation. Among the surviving compilations, the one known by its opening words as the Plough Star gathers earlier material into a systematic arrangement, sorting some dozens of stars and star groups into 3 broad bands of sky named for 3 gods, listing the dates on which each first appears in the dawn twilight, and giving simple rules for the length of daylight through the year. Cuneiform astronomy grew steadily more numerical over the following centuries, and by the last few hundred years before the Common Era, Babylonian scribes were recording positions of the moon and planets against a set of reference stars strung along the zodiac, in a system of 12 equal divisions that passed westward and remains in use for naming the constellations of the ecliptic. Their tablets also preserve long runs of observation, night after night, of the kind that later astronomers would mine for the slow drifts that only decades of data reveal. Chinese astronomers built a parallel and largely independent map. Traditions associated with several early schools of observation were eventually combined in the 3rd century of the Common Era into a single scheme dividing the sky into a few hundred small asterisms containing well over 1,000 stars, most of them groupings of only 3 or 4 points and named after offices of the imperial court, granaries, chariots, wells, and market stalls. Around the celestial pole lay 3 enclosures, and along the path of the moon lay 28 lodges of unequal width, used to measure position much as degrees were used further west. A manuscript recovered from a sealed cave at Dunhuang, drawn in the 7th century, unrolls this sky across a series of panels and marks more than 1,000 stars in colored ink. Hipparchus, working on roads in the 2nd century before the Common Era, brought Greek geometry to bear on the same material. Comparing his own measured position for a bright star in Virgo with a value recorded roughly a century and a half earlier at Alexandria, he found a shift along the ecliptic that could not be attributed to error, and concluded that the whole framework of stars slides slowly against the equinoxes at a rate of about 1 degree per century. He is credited with compiling a catalogue of his own and with grading stars into 6 ranks of brightness, the 1st rank for the most conspicuous and the 6th for those barely visible. His book has not come down to us intact, though fragments of what appear to be his coordinates have been read in recent years from a parchment that was scraped clean and written over. Ptolemy assembled the great synthesis at Alexandria in the 2nd century of the Common Era, and the Star Catalogue occupies 2 books of the work later known by its Arabic name, the Almagest. Just over 1,000 stars appear there, arranged into 48 figures, each entry giving a position in ecliptic longitude and latitude, a magnitude on the 6-step scale, and a description of where in the figure the star sits: at the left shoulder, in the mouth, on the bend of the river. Scholars have argued for centuries about how much of this Ptolemy measured himself, since many of the positions look like Hipparchus values carried forward with a precession constant that was slightly too small. Whatever its provenance, the list served as the standard reference for 1,400 years. Astronomers writing in Arabic inherited the catalogue, corrected it, and gave much of the sky the names it still carries. Al-Sufi produced in the 10th century a book of fixed stars that illustrated every constellation twice, once as it appears on a globe and once as it appears reversed in the sky, revised the magnitudes from his own inspection, and mentioned a small patch of cloud in Andromeda, along with a bright cloud reported by sailors far to the south. Star names in common use today, among them Aldebaran the follower, Deneb the tail, Altair and Rigel, are shortened forms of the Arabic descriptions of position within a figure, worn smooth by centuries of Latin transcription. At Samarkand in the 15th century, a Timurid prince with a serious interest in astronomy built an observatory around a meridian arc of enormous radius sunk into a trench and gathered mathematicians there to remeasure the sky. Their tables gave fresh positions for more than 1,000 stars, the first substantially new catalogue since antiquity rather than an update of an old one, and the work reached Europe in manuscript and was eventually printed at Oxford. Tycho Brahe raised naked eye measurement to its limit on the island of Hven, where the Danish crown granted him land and revenue, and he built a house of observation with a second, sunken station nearby to shield his instruments from the wind. He commissioned quadrants and sextants of unprecedented size and stability, checked each one against the others, corrected systematically for refraction near the horizon, and repeated every observation until the scatter told him what it was worth. His positions are good to something like a minute of arc, several times better than anything before, and the catalogue of about 1,000 stars that grew out of them was published after his death by Kepler, bound into the tables named for their imperial patron. Bayer's Atlas of 1603 did something simpler, and, for daily use, more durable. A lawyer in Augsburg with a taste for celestial cartography, he engraved each constellation on its own plate at a generous scale, drew the figures lightly so the stars remained legible beneath them, and labeled the stars within each figure using letters of the Greek alphabet, roughly in order of brightness, continuing into Roman letters when the Greek ran out. The scheme spread quickly because it was easy to speak aloud and easy to print. He also included a plate of the far southern sky, filled with 12 new figures based on observations made by 2 Dutch navigators during a voyage to the East Indies, which is how a toucan, a chameleon and a flying fish came to occupy the region around the southern pole. Johannes Hevelius, a brewer and civic official in Danzig, spent decades observing from a platform built across the roofs of 3 adjoining houses, and insisted to the end on open sights rather than telescopic ones, arguing that a trained eye at a long instrument lost nothing. Halley travelled north to test the claim and found the old man's positions genuinely good, though the method died with him. A fire destroyed much of his observatory in 1679, yet the catalogue survived, and his widow Elizabeth, who had observed alongside him, saw the atlas and its list of more than 1,500 stars through to publication after his death. Several of the constellations he invented to fill the gaps between the old figures, among them the lynx, the shield, and the hunting dogs, are still recognized. Halley himself had sailed south in his early 20s to St. Helena, where cloud and rain frustrated him for months, and returned with the first catalogue of southern stars measured with telescopic assistance. At Greenwich, meanwhile, John Flamsteed applied telescopic sights and a clock-driven regime of transit observations to the northern sky over some 40 years, working in equatorial coordinates and achieving accuracies measured in seconds of arc rather than minutes. His full catalogue of nearly 3,000 stars appeared only after his death, prepared for the press by his widow and his assistants, following a bitter episode in which an unauthorized edition had been printed from his data, and most of the copies he could obtain were burned. The running numbers now attached to his name were added by a later French editor. Cataloguing had by then become something more than a way of finding one's place among the figures. Positions recorded to a few seconds of arc, set beside positions recorded 14 centuries earlier, revealed in 1718 that Sirius, Arcturus and Aldebaran had shifted from where Ptolemy placed them by amounts too large to blame on ancient sloppiness, which meant the fixed stars were not fixed at all but moving, each on its own course, at rates the catalogues could measure. Motion among the stars sharpened a question that had been waiting for 2,000 years, because a star that drifts is a star at some particular distance, and nobody could say what that distance was. The geometric method had been understood since antiquity and required no new idea at all, only a steadier hand than anyone yet possessed. A nearby object viewed from 2 separated vantage points appears to shift against a more distant background, as a finger held up before the face jumps from side to side when one eye closes and then the other, and the amount of the shift depends on how far away the finger is held. For the stars, the 2 vantage points were the Earth in January and the Earth in July, separated by the full width of its orbit, and the background was the general throng of the sky. Aristarchus of Samos had used the absence of any such shift to argue about the arrangement of the cosmos, and Copernicus faced the same objection in the 16th century. If the Earth truly circled the Sun, the stars ought to sway with the seasons, and they plainly did not. Tycho Brahe, whose naked eye positions were good to a minute of arc or better, pressed the point hard. Either the Earth stood still, or the stars lay at distances so great that their sway fell below anything his quadrants could register, which to him seemed an absurd waste of space. Both alternatives were logically clean. Only one of them was correct, and settling the matter took instruments that would not exist for another 2.5 centuries. Robert Hooke made an attempt in the 1670s, with a telescope mounted vertically through his roof, pointed at Gamma Draconis, a star that passes almost exactly overhead in London, and therefore suffers the least distortion from the atmosphere. He gathered only a handful of observations before illness, and the awkwardness of the apparatus defeated him, and the result he published was an artifact. James Bradley and Samuel Molyneux took up the same star from Kew in 1725 with a zenith sector built to a far higher standard, and found a genuine annual displacement of about 20 seconds of arc, which was much larger than any plausible parallax and, more troublingly, ran 3 months out of step with what parallax would produce. Bradley worked out that he was seeing the aberration of light, the small tilt that the observer's own orbital motion imposes on the direction of an arriving ray, and he later teased out nutation, the slow nodding of the Earth's axis. Both discoveries proved the Earth's motion beyond argument. Neither gave a distance, and Bradley concluded that whatever parallax Gamma Draconis possessed had to be smaller than about a second of arc. That figure sets the difficulty in its proper light. A second of arc is the angle subtended by a small coin seen from a distance of 4 kilometers, and the shifts astronomers were hunting amounted to fractions of that, buried beneath aberration 20 times larger, beneath refraction that changes with temperature and pressure, beneath the flexure of brass tubes warming and cooling through a night, and beneath the proper motion that carries a star steadily across the sky year after year, in a straight line, while parallax traces a small ellipse and returns each 12 months to where it began. Choosing the right star mattered more than any refinement of technique. Brightness offered one clue to nearness, but a brilliant star might simply be an intrinsically luminous one far away. Large proper motion offered a better clue, since a star that appears to travel quickly across the background is likelier to be close, in the same way that a near bird crosses the window faster than a distant aircraft. Giuseppe Piazzi had drawn attention to a modest double star in Cygnus, catalogued as 61 Cygni, which shifted position by more than 5 seconds of arc every year, the swiftest known at the time, and it acquired the nickname of the Flying Star. Friedrich Wilhelm Bessel at Königsberg took that star as his target. His instrument was a heliometer from the Munich workshop associated with Joseph Fraunhofer, a refractor whose object glass had been sawn cleanly in half so that the two semicircles could slide against each other on a calibrated track, producing 2 images of the field that the observer brought into coincidence with the amount of sliding read off as an angle. The design measured small separations between neighboring stars far better than it measured absolute positions, which suited the task exactly, because Bessel did not need to know where 61 Cygni was in any grand sense. He needed only its distance from 2 faint stars in the same field, presumed remote and therefore effectively fixed. Between August of 1837 and October of 1838, he took hundreds of such readings and found that the separations swelled and shrank through the year by about 1/3 of a second of arc. Announced in a letter to John Herschel and published before the year was out, the number implied a distance of some 10 light-years, and the Royal Astronomical Society awarded him its gold medal. At the Cape of Good Hope, Thomas Henderson had already gathered the data that would give a second answer, though he did not yet know it. During 1832 and 1833, he observed Alpha Centauri, a bright southern star with a large proper motion, using the observatory's mural circle, and then returned to Britain in poor health, carrying his notebooks with him. Reduction was slow. He wanted confirmation before committing himself, and his paper appeared in January of 1839, a few weeks after Bessel's. His parallax came out near a full second of arc, larger than any other yet found, placing the star at a little over 4 light-years and establishing it as the nearest stellar system known. Henderson became Astronomer Royal for Scotland and died young, his priority lost by a matter of months to a rival who had begun the work later and finished it first. Friedrich Georg Wilhelm Struve, working at Dorpat with the great Fraunhofer refractor and a Pfeiler micrometer, had been measuring Vega across the same years. His published values wavered between one paper and the next, the figure he eventually settled on being roughly twice what is now accepted, and contemporaries treated his result more cautiously than Bessel's. He had nonetheless been among the first to look, with a sound method, at a genuinely near star, and he went on to direct the new observatory at Pulkovo, which became for a time the best equipped in the world. 3 answers arriving within about 2 years was no coincidence. Optical glass of uniform quality had become available in usable sizes. Dividing engines could rule a circle to a fineness that matched the eye's ability to read it. Pendulum clocks kept time well enough to time a transit to fractions of a second. And the mathematics of error had matured to the point where an observer could state not only a value, but the uncertainty attached to it, and could combine hundreds of imperfect readings into one defensible number. Bessel, in particular, was a formidable analyst, and his willingness to publish his probable error persuaded readers who would have distrusted a bare assertion. What the results meant took some time to absorb. Sunlight reaches the Earth in about 8 minutes. The light of Alpha Centauri has been traveling for more than 4 years when it arrives, and that of 61 Cygni for over 11. Expressed in the older unit, these stars lay hundreds of thousands of times further away than the Sunday. The light year came into general use during the 19th century as a way of saying such things without unwieldy strings of digits, and it carried an implication that unsettled some readers, since to look at a star is to see it as it was, never as it is. Professional astronomers preferred a unit built from the measurement itself. In 1913, the British astronomer Herbert Hall Turner proposed the parsec, the distance at which one astronomical unit would subtend 1 second of arc, equal to about 206,000 times the Earth-Sun separation, or 3¼ light-years. Distance in parsecs is simply 1 divided by the parallax in seconds of arc, which spares the working astronomer an arithmetic step. No star lies within a parsec of us. The nearest, a dim red companion to the Alpha Centauri pair identified in 1915, sits at about 1 3/10. Photography turned the technique into an industry, since plates could be measured at leisure and by anyone, and by the middle of the 20th century, a few thousand parallaxes had been accumulated, with the atmosphere setting a floor near 1/100th of a second of arc. Instruments carried above the air lifted that floor. The Hipparcos satellite, launched in 1989, produced accurate parallaxes for roughly 100,000 stars, and the Gaia mission, launched in 2013, has done the same for well over 1 billion, reaching precisions measured in millionths of a second of arc. Every larger distance in astronomy still rests, in the end, on this small seasonal wobble and on the width of one orbit. A glass prism had been splitting sunlight into colors since Newton's experiments in the 1660s, and for well over a century, nobody saw anything in that band of color but a smooth gradation from red to violet. The reason lay in the apparatus rather than in the light. Newton admitted his sunbeam through a round hole, so the spectrum he produced was a series of overlapping circular images, each blurring into the next. When the English chemist William Hyde Wollaston replaced the hole with a narrow slit in 1802, the colors arranged themselves more sharply, and he noticed 7 dark gaps crossing the band. He took them for natural boundaries between the colors and set the observation aside. Joseph von Fraunhofer came to the same gaps from the direction of the workshop rather than the laboratory. Trained as a mirror and lens maker, orphaned young, injured when the building he was apprenticed in collapsed, he ended up directing the optical works at a former monastery at Benediktbayern in Bavaria, where he was trying to make achromatic lenses of a quality nobody else could reach. That work required him to measure how strongly a given batch of glass bent light of one particular color. And to do that, he needed a color he could return to exactly. Around 1814, hunting for such a reference, he built a spectrometer combining a slit, a prism, and a small telescope, and pointed it at the Sunday what appeared was not 7 gaps, but hundreds. Fraunhofer counted well over 500 dark lines ruled across the solar spectrum, mapped their positions, and gave letters to the strongest of them, beginning at the red end with A and running through B, C, D, E, F, G, and H. The letters are still in use. He noticed that his D line, a close pair in the yellow, fell exactly where a bright yellow line appeared when he burned certain substances in a lamp flame, though he could not say why a bright emission and a dark absence should share a position. Later he ruled fine grooves into metal and glass to make diffraction gratings, which allowed him to attach actual wavelengths to the lines rather than mere positions on a scale. Turning the instrument away from the sun took more patience, since starlight spread into a spectrum is very faint. Fraunhofer managed it nonetheless. Venus and the Moon gave him the solar pattern back, unchanged, which made sense for reflected sunlight. Sirius gave him something else, a spectrum crossed by a few broad, strong bands, quite unlike the sun's crowded ruling. Other bright stars showed still other arrangements. The stars, whatever else they were not all alike, and something about them was written in a language nobody could yet read. Fraunhofer died in 1826, at 39, of tuberculosis, with the lines named after him and unexplained. The reading came from chemistry. Through the 1840s and 50s, various workers noticed that each substance dropped into a flame produced its own set of bright colors, and by 1859, Gustav Kirchhoff and Robert Bunsen at Heidelberg had assembled the pieces into a working theory. Bunsen's burner gave a flame almost without color of its own. Kirchhoff supplied the prism and the reasoning. They passed sunlight through a sodium flame and expected the flame's yellow emission to fill in the dark solar D line. Instead, the line grew darker. A gas, Kirchhoff concluded, absorbs precisely the wavelengths it would emit if it were glowing on its own, and a cool gas, standing in front of a hot, continuous source, will therefore stamp its own signature into that source as a set of dark lines. 3 rules followed, and they hold today. A hot, dense body radiates a continuous spectrum with no lines. A hot, thin gas radiates only at particular wavelengths. A continuous spectrum seen through a cooler, thin gas shows dark lines at those same wavelengths. Since the pattern belongs to the element and not to the circumstances, the dark lines in sunlight amounted to a chemical analysis of the solar atmosphere performed at a distance of 150 million kilometers. Kirchhoff and Bunsen identified sodium, iron, magnesium, calcium, and several other familiar metals in the Sun within a few years, and their method soon turned up two new elements in terrestrial minerals, cesium and rubidium, both named for the color of their brightest lines. One line refused to match anything on Earth. During a total solar eclipse in 1868, observers including Pierre Janssen and, working separately, Norman Lockyer, found a yellow emission line close to sodium's pair but not coincident with it. Lockyer, with the chemist Edward Frankland, argued that it belonged to an element unknown in any laboratory and gave it a name drawn from the Greek word for the Sunday. Helium was not isolated on Earth until 1895, when William Ramsay extracted it from a uranium mineral and found the yellow line waiting in it. In a private observatory at Tulse Hill in South London, William Huggins and his wife Margaret Lindsay Huggins carried the method out to the stars in earnest, working through the 1860s on spectra of Betelgeuse, Aldebaran and others, and finding hydrogen, sodium, iron, calcium, and magnesium in objects that no chemistry could ever sample. The universe, in other words, was made of ordinary stuff. Huggins also turned his prism on a nebula in Draco and saw not a continuous band with dark lines, but a few isolated bright ones, the mark of glowing gas rather than a mass of unresolved stars. In 1868, he measured the slight shift of a hydrogen line in Sirius and derived a speed of recession, opening the way to velocities along the line of sight for anything bright enough to photograph. Sorting the stars by their spectra began with Angelo Secchi, a Jesuit priest working at the Roman College, who examined thousands of them through the 1860s and grouped them into a handful of broad types: white stars with strong hydrogen, yellow ones with many fine metallic lines like the Sun, and redder ones showing broad dark bands. The next advance was photographic. Henry Draper, a physician and amateur astronomer in New York, obtained the first photograph of a stellar spectrum of Vega in 1872. Placing a large, thin prism in front of the telescope objective turned every star in the field into a small streak of spectrum on the same plate, so that hundreds could be recorded in a single exposure. Draper died in 1882, and his widow, Anna Palmer Draper, endowed a memorial at Harvard College Observatory to continue the work. Edward Pickering, the director, built the program around a staff of women employed to measure and classify the plates at rates of pay well below what men in comparable positions received. Williamina Fleming, who had worked in Pickering's household before joining the observatory, devised the first Harvard scheme, sorting spectra alphabetically from A to N according to the strength of the hydrogen lines, and classified more than 10,000 stars for the first Draper catalogue published in 1890. Antonia Maury, a niece of Henry Draper, took a different approach on the brighter northern stars, building a scheme of numbered groups and adding lowercase divisions to record whether a star's lines were hazy, average, or unusually sharp and narrow. Pickering thought the refinement unnecessary. It was not. Those narrow lines mark stars of great luminosity, and the distinction Maury noticed would later become the second axis of stellar classification. Annie Jump Cannon joined the observatory in 1896, having studied physics and astronomy at Wellesley and Radcliffe, and largely deaf since an illness in her youth. Working on the southern stars, she found that Fleming's alphabet made better sense, rearranged and pruned. Several letters were redundant, and the rest fell into a smooth progression if ordered O, B, A, F, G, K, M. She subdivided each class by tenths, so that a star could be called B5 or G2, and the sequence proved to run continuously from the hottest stars to the coolest. Her speed was extraordinary for such work, and over her career she classified something on the order of 350,000 stars by eye. The core of them, appearing in the Henry Draper Catalogue, issued between 1918 and 1924. Why the sequence ran that way became clear only afterwards, when Meghnad Saha's work on ionization in hot gases showed that the presence or absence of a given line depends chiefly on temperature rather than on abundance, and when Cecilia Payne, in a doctoral thesis at Harvard in 1925, applied that physics to the Harvard classes and concluded that stars are overwhelmingly hydrogen and helium. The letters Cannon had arranged for tidiness turned out to be a thermometer, reading from around 40,000 degrees down to under 3,000, and they remain in use, extended at the cool end for objects fainter and redder than any star Fraunhofer could have reached. Two astronomers, working apart and from unlike materials, arrived within a few years of each other at the same picture of the sky, and the picture has organized the subject ever since. Ejnar Hertzsprung, a Danish chemical engineer by training who had turned to photographic photometry, noticed that Antonia Maury's narrow-lined stars at Harvard, which she had marked with a lowercase c, moved very little against the background over the years. Small apparent motion suggested great distance, and great distance, combined with easy visibility, suggested enormous output of light. In notes published in 1905 and again 2 years later, in a photographic journal that few astronomers read, he set out the consequence. Among stars of one and the same spectral class, there exist two quite separate populations, one feeble and one luminous. Henry Norris Russell, at Princeton, reached the point from the direction of distance measurement. He had spent years accumulating parallaxes, and with distances in hand he could convert apparent brightness into the true output of each star, then plot that quantity against the Harvard spectral letter. When he showed the resulting chart to the Royal Astronomical Society in 1913, the scattered points were not scattered at all. Most of them lay along a single diagonal band running from hot and brilliant at one corner to cool and faint at the other, with a second group of cool stars perched high above the band, far brighter than their temperature alone would predict. Convention placed temperature along the horizontal axis with the hottest classes at the left, an inheritance from the old habit of listing spectral types in Cannon's order, and brightness up the vertical axis. Astronomers came to call the diagonal band the main sequence, the cool, luminous group the giants, and, once white dwarfs had been recognized, the sparse population at the lower left by that name. What matters as much as the occupied regions is the emptiness elsewhere. Almost no stars sit between the main sequence and the giants. Almost none lie below the sequence except the dwarfs. A star cannot take any combination of temperature and brightness it likes. Russell's first reading of his own diagram was mistaken, and the mistake left a mark on the vocabulary. He supposed that a star began as a swollen, cool object, contracted and heated until it reached the top of the main sequence, then slid down the sequence as it cooled and faded, so that the diagonal band was a path traveled rather than a place inhabited. On that picture, the giants were young, and the faint red stars were old. The words giant and dwarf, coined for the two branches, survived the theory that produced them. Sorting out what the diagram actually meant required a quantity the diagram itself did not contain, which was mass. Weighing a star is possible only when it pulls on something whose motion can be watched. And for that, astronomy depended on double stars. William Herschel, at the beginning of the 19th century, had followed pairs such as the components of Castor long enough to see them curve about one another, establishing that some doubles are bound systems and not chance alignments. Newton's generalization of Kepler's third law then gives the total mass of such a pair directly from the period of the orbit and its true size, and the true size follows from the angular size once the distance is known. Three kinds of pair each yielded something different. Visual binaries, wide enough to be resolved, gave the orbit in the sky, but only the combined mass, unless the two stars could be tracked separately against more distant background. Spectroscopic binaries, too close to separate by any telescope, betrayed themselves in the spectrum. At Harvard in 1889, the lines of Mizar were found to double and rejoin in a regular cycle, the signature of two bodies alternately approaching and receding, and measurement of that rhythm gives orbital speeds. Eclipsing pairs, of which Algol had long been the familiar case, add the missing geometry, since a system that eclipses must be seen nearly edge-on, and the shape and duration of the dimming yield the sizes of both stars as well. Combine the spectroscopic velocities with the eclipse timing, and the individual masses and radii both fall out. By the early 1920s, enough such systems had been measured for Arthur Eddington to plot mass against luminosity, and in 1924 he published the relation he found. Brightness climbs far faster than weight. Doubling the mass of a star multiplies its output roughly tenfold. Across the ordinary range, the luminosity follows something close to the 3.5 power of the mass. Eddington had expected giants and main sequence stars to fall on separate curves, and was struck to find them on much the same one, which told him the relation arose from something deep in the structure of a gaseous sphere rather than from any particular stage of life. That something is the balance every star must keep. Each layer is squeezed by the weight of everything above it and must push back with equal pressure, so a heavier star has a hotter, denser core, simply because more material is pressing inward. Nuclear reactions respond to temperature with extraordinary sensitivity. A modest rise in central heat, producing a large rise in the rate of energy release. And the star can do nothing with that energy except pass it outward and radiate it away. Mass sets the central conditions set the rate of burning, and the rate of burning sets the brightness. Naming the reactions took longer than describing their effects. 19th century physics had offered gravitational contraction as the sun's fuel, which gave it a life of a few tens of millions of years and put astronomy at odds with geologists reading far longer histories in rock. Speaking to the British Association in 1920, Eddington pointed to Francis Aston's precise atomic weights, which showed that 4 hydrogen nuclei together weigh a little more than 1 helium nucleus, the surplus amounting to about 0.7%. Converting even a fraction of a star's hydrogen on those terms would supply its radiation for billions of years, and Eddington said plainly that the energy of the stars was locked in this manner, and that mankind was not far from learning to release it. An objection stood in the way. 2 protons repel each other fiercely, and the center of the Sun, at something near 15 million degrees, seemed far too cool for them to meet. George Gamower's treatment of quantum tunneling in 1928 removed the difficulty by showing that particles occasionally pass through barriers they cannot climb, and within a year, Robert Atkinson and Fritz Houtemans had applied the idea to stellar interiors. Through the 1930s, the specific chains were worked out, Hans Bethe and Charles Critchfield describing the sequence by which protons fuse step by step into helium, and Bethe together with Carl Friedrich von Weizsäcker describing an alternative route in which carbon, nitrogen and oxygen act as catalysts and are returned unchanged at the end. Which of the 2 routes dominates depends, again, on mass. In the Sun, and in stars lighter than it, the direct proton chain supplies nearly all the output, above roughly 1 1/3 times the solar mass the catalytic cycle takes over, and because its rate responds to temperature far more sharply, it concentrates energy release into a small central region and stirs that region into convection, giving heavy stars a quite different internal arrangement from light ones. From the same relation follows the arithmetic of stellar lifetimes, and it runs against intuition. Fuel supply is roughly proportional to mass, so a star 10 times heavier begins with 10 times as much hydrogen, but it spends that store some thousands of times faster. A star of 10 solar masses exhausts its core hydrogen in a few tens of millions of years, while the Sun has some 10 billion years in that phase and is a little under halfway through. Reduce the mass to 1/3 of the Sun's, and the reserve lasts far longer than the present age of the universe, so that no such star has yet finished burning. Boundaries appear at both ends. Below about 8% of the Sun's mass, contraction halts before the center grows hot enough for hydrogen fusion to become self-sustaining, and the object settles into a slow cooling as a brown dwarf. At the other extreme, radiation streaming outward from a very hot core begins to push on the overlying gas hard enough to drive it off. The limit Eddington first calculated, and the heaviest stars catalogued, run to something over 100 times the Sun rather than to any larger figure. Between those bounds, the main sequence is best understood as a mass sequence. A star's place along it announces its weight, and its weight has already decided how brightly it will shine and how briefly. Constancy was, for a very long time, part of what the word star meant. Planets wandered, comets came and went, meteors flared for a second and were gone, but the fixed stars held their places and, it was assumed, their brightness. That assumption survived in Europe until the late 16th century, when the Frisian astronomer David Fabricius, watching the sky in 1596, noted a star in the constellation Cetus that he had used as a reference point and then found missing on a later night. He supposed at first that he had made an error, and only after the star returned did the possibility settle that a single point of light might rise and fade on its own schedule. Johannes Holwada, observing the same object some 40 years later, established that the cycle repeated with a length of roughly 11 months, and Hevelius gave the star the name Mira, the Wonderful One, which it still carries. Its behavior is now understood as pulsation on a large scale, a cool giant, swollen to a size that would swallow the inner solar system, expanding and contracting over about 330 days. At maximum, it is an easy naked eye object, and at minimum, it needs a telescope, a swing in visual light far greater than the swing in total energy output, because as the surface cools, much of the radiation shifts into the infrared, and molecules forming in the outer layers absorb what remains in the visible range. Algol, in Perseus, changes in a different manner and on a different clock. Its variation was recorded by Geminiano Montanari in the 17th century, but the pattern was pinned down in the 1780s by John Goodricke, a young English observer who was deaf from early childhood and who worked in close company with his neighbour Edward Pigott. Goodricke timed the dimming to a cycle of about 2 days and 21 hours, noticed that the star held steady for most of that interval, and then dropped sharply for a few hours before recovering, and proposed that a dark body might be passing in front of it. Confirmation had to wait more than a century, until spectroscopic measurement of the star's motion towards and away from the Earth revealed the companion by its gravitational pull exactly as the eclipse picture required. Goodricke and Pigott went further in the years that followed, identifying variability in Eta Aquilae and in Delta Cephei, the second of which lent its name to an entire class. Cepheid variables rise quickly and fall more slowly, with a sawtooth-like curve rather than the flat plateau and sudden dip of an eclipsing pair. And Delta Cephei itself runs through its cycle in about 5 1/3 days, changing by roughly a factor of 2 in visual brightness. Nothing in the 18th century could explain the difference in kind between such a star and Algol, but the distinction between stars eclipsed by companions and stars genuinely changing in themselves was already implicit in the shapes of the curves. Systematic study required both a nomenclature and a method. Friedrich Argelander, working at Bonn in the middle of the 19th century, supplied both, assigning capital letters beginning at R to the variables of each constellation, and devising a technique of estimating brightness in small steps against neighboring stars, which allowed observers without instruments of any refinement to produce usable measurements. Variable star watching became one of the few branches of astronomy where patient amateurs contributed data the professionals could not gather for themselves, since the work demanded thousands of nights and many pairs of eyes, and an association founded in the United States in 1911 has been collecting such estimates ever since. Photography altered the scale of the enterprise. At Harvard College Observatory, a program of repeated photographic surveys accumulated glass plates by the tens of thousands, each recording a field of sky at a particular moment, and comparing 2 plates of the same field, taken on different nights, turned the hunt for variables from an act of vigilance into an act of inspection. A staff of women was employed to examine, measure, and classify these plates, and among them was Henrietta Swan Leavitt, who took charge of the variable star work and who established the standards by which stellar magnitudes on the plates were determined. Among the fields photographed repeatedly from the observatory's southern station in Peru were the Magellanic Clouds, 2 patches of the southern sky that were then of uncertain nature. Leavitt found variables in them in great numbers, publishing lists that ran into the hundreds, And in doing so, she noticed a pattern that no one studying variables scattered across the local sky could have noticed. Within the small Magellanic Cloud, the Cepheids with longer cycles were consistently the brighter ones, and the correspondence between cycle length and apparent brightness was tight enough to be drawn as a line. Since every star in that cloud lay at very nearly the same remove from the Earth, differences in how bright they appeared had to reflect differences in how much light they actually emitted. Her result, published in 1912 on the basis of 25 of these stars, converted a period into a luminosity. A Cepheid anywhere in the sky could be watched through a few cycles, its period read off, its true output inferred from the relation, and its distance then obtained by comparing that output with how faint it looked. The one thing missing was a 0 point, since the Magellanic Clouds themselves were of unknown remoteness, so the ladder needed a bottom rung anchored in geometry. Ejnar Hertzsprung supplied a first calibration the following year using the statistical motions of nearby Cepheids in the Milky Way, and others refined the figure over the decades that followed. Harlow Shapley applied the method to globular clusters, using the short period variables they contain, and found that the clusters were spread through a region far larger than the star system as it had been imagined, arranged around a center lying not near the Sun but tens of thousands of light years away in the direction of Sagittarius. The Sun's demotion from any central position followed directly from a class of pulsating star and a photographic plate. Shapley's absolute numbers were too large, partly because interstellar dust dims distant objects, and partly because the variables he used were not all of one kind, but the geometry he sketched has survived. Working at Mount Wilson in 1923, Edwin Hubble found a Cepheid on a plate of the Andromeda Nebula, measured its period, and derived a distance that placed the nebula altogether outside the Milky Way. The spiral nebulae, argued over for a century, were resolved into other galaxies, and the same relation that had mapped one star system began measuring the separations between them. Hubble's value fell well short of the modern figure of some 2.5 million light-years, and the reason emerged in the 1950s, when Walter Baade distinguished two populations of stars and showed that the classical Cepheids of the spiral arms follow a different period to luminosity relation than the older variables Shapley had used. Correcting the confusion roughly doubled the accepted scale of the universe at a stroke, a reminder that every error in a low rung is inherited intact by every rung above it. Explanation of the pulsation itself came slowly. Arthur Eddington proposed that such a star acts as a heat engine with a valve, a layer that becomes more opaque when compressed, traps the outgoing radiation, builds up pressure, pushes the envelope outward, then releases the stored heat and lets the layer fall back. Later work identified the layer as a zone where helium is partly stripped of its second electron, and the stars that pulsate in this way occupy a narrow, nearly vertical band across the diagram of luminosity against temperature, crossed by stars of the right mass at the right moment in their evolution. RR Lyrae stars sit lower in that band, cycling in less than a day at a fairly uniform luminosity, and they serve as distance markers within our own galaxy and its immediate neighbors. Beyond the reach of individual Cepheids lie other indicators, chief among them the exploding white dwarfs whose peak output can be standardized, and beneath the whole structure lies trigonometric parallax, now measured by spacecraft for more than 1 billion stars, which pins the lowest rung with a precision Leavitt could not have obtained. The chain from a star that brightens and dims over a few days to the separation between clusters of galaxies remains one long argument, each link tested against the ones below it. Size was inferred before it could be measured. Once astronomers had a law relating the energy radiated by each square meter of a hot surface to its temperature, and once spectroscopy gave them temperatures, a star's total output could be divided by the output per unit area to yield a surface area, and from that, a radius. The calculation was indirect, resting on distance estimates that were themselves shaky, but the result was unambiguous in kind. Certain cool stars poured out so much light at so low a temperature that the only way to reconcile the two figures was to make them physically huge. Hertzsprung and Russell had already separated giants from dwarfs on those grounds. What remained was to see whether a telescope could confirm, by direct measurement of an angle on the sky, what the arithmetic had implied. Hippolyte Fizeau had suggested the method in the 1860s, pointing out that if the light from a single star reached a telescope through two separated apertures, the interference fringes formed where the beams recombined would fade as the separation grew, and the separation at which they vanished would depend on the apparent width of the source. Albert Michelson tested the principle at the Lick Observatory in 1891 on the satellites of Jupiter, whose disks were already known, and found it sound. Applying it to a star meant working with an angle thousands of times smaller, which meant baselines longer than any telescope aperture then in existence, and so the technique waited for a mounting sturdy enough to carry mirrors on a beam above the tube of a large reflector. That arrangement was built at Mount Wilson and fitted to the 100-inch telescope, a steel beam some 6 meters long carrying outer mirrors that could be slid apart while the observer watched the fringes at the eyepiece. In the closing weeks of 1920, Michelson and Francis Pease turned it on Betelgeuse, the red star in the shoulder of Orion, and found that the fringes disappeared at a separation corresponding to an angular diameter of roughly 0.05 of a second of arc. Converting that angle into kilometers required a distance, and the distance was poorly known, but even a rough figure gave a body several hundred times wider than the Sunday. A handful of other red stars followed over the next few years, and the list stalled there because the method demanded steady air, a bright target, and patience beyond what most observers could sustain. A second route to the same numbers ran through the moon. As the lunar limb sweeps across a star, the light does not switch off cleanly, but ripples through a brief pattern of diffraction fringes, and the shape of that pattern depends on the angular size of the source, so a photometer recording the fading at high speed can extract a diameter from an event lasting a fraction of a second. Occultations are unrepeatable, confined to stars near the moon's path and to observers in the right band of the Earth's surface, but they need no special interferometer, and they gave independent checks on the few stars large enough to be within reach. Eclipsing pairs offered something different again, a geometry rather than an angle. When one star passes in front of another, the timing of the contacts, the moment the dimming begins, the moment it becomes total, the moment it ends, encodes the radii of both bodies expressed as fractions of the separation between them, and the separation follows from the orbital period and the masses. Certain systems containing a supergiant and a small hot companion proved particularly informative because the companion's light, filtering outward through the extended upper layers of the larger star before disappearing behind it, revealed the structure of those layers line by line as the eclipse progressed. Some of these systems run on cycles of years or decades, so a single, well-observed eclipse could occupy the working lives of 2 generations of observers. Robert Hanbury Brown and Richard Twist developed a wholly different instrument in the 1950s and 60s, one that compared not the light waves themselves, but the fluctuations in the rate at which photons arrived at 2 widely spaced detectors. Their intensity interferometer at Narrabri in New South Wales used 2 mirrors of crude optical quality running on a circular track, insensitive to the atmospheric blurring that had made the older method so exhausting, and with it they measured the diameters of several dozen hot blue stars, whose angular sizes were far below anything the Mount Wilson beam could have resolved. The technique suited bright blue objects and could not be pushed to faint ones, but it settled the sizes of the main sequence stars against which the giants had to be compared. Modern arrays returned to combining the light waves, now with several separate telescopes, evacuated pipes to carry the beams, and delay lines that adjust path lengths by micrometers to keep the interference stable. Instruments of this kind on Mount Wilson and in the Chilean desert have resolved not merely the widths of nearby supergiants, but structure across their faces, patches brighter and darker than their surroundings, shifting over months. Such patches match what theory predicts for a star whose outer envelope is so distended that convection organizes itself into a few enormous cells, rather than the millions of small granules that cover the Sun, each cell rising, spilling, and cooling over a timescale of years. Measuring the edge of such a star turns out to be a question of definition. The gas does not stop, it thins, and the height at which it becomes opaque depends on what is absorbing. So the same star, observed in a band where titanium oxide or water vapor absorbs strongly, appears wider than it does in a window between those bands. Limb darkening complicates matters further, since the disk is fainter at its rim than at its center, and an interferometer fitting a uniform disk to its fringes will return a slightly different figure than one, allowing for the fading. Published diameters therefore carry a model with them, and comparing 2 values from different decades often means comparing 2 sets of assumptions as much as 2 observations. Betelgeuse illustrates the difficulty in full. Its angular diameter is among the largest of any star, yet its distance is stubbornly uncertain, partly because the star is bright enough to saturate the detectors built for parallax work, and partly because those wandering surface patches shift the apparent center of light from year to year, blurring the very displacement the measurement depends on. Radio observations of its extended envelope have helped, and the figures now used place it somewhere in the region of 600 light-years, which makes its radius several hundred times that of the Sun, large enough that a body of that size centered on the Sun would swallow the orbit of Mars. Its brightness varies irregularly, and during the winter of 2019 and the following spring, it faded to a degree that drew wide attention, later attributed to a combination of surface cooling and dust condensing in material the star had shed. Antares, the red star at the heart of Scorpius, has been measured by the same methods and by occultation, and its angular diameter is comparable. A hot blue companion orbits it at a distance great enough that light from the smaller star passing through the supergiant's outer atmosphere can be studied directly, which has allowed astronomers to trace where the gas becomes turbulent and where it begins to flow outward for good. VY Canis Majoris sits in a different category again, a cool hypergiant embedded in a knotted cloud of its own making, detectable by the radio emission of water and silicon monoxide molecules in the outflow, and by the reflected light of dust that surrounds it. Estimates of its radius run to well over 1,000 times the Sun's, which would carry its surface out past the orbit of Jupiter, and light would need something close to 2 hours to cross it. What holds all of these stars together is thin almost beyond ordinary comparison. A supergiant may carry 15 or 20 times the Sun's mass, but it spreads that mass through a volume perhaps 1 billion times greater, so its average density falls to a small fraction of 1/1,000,000th of a gram in each cubic centimeter, tens of thousands of times less than the air at sea level. Nearly all the mass sits in a dense core no wider than the Earth's orbit, and the enormous envelope above it is a rarefied haze held loosely by gravity that has weakened with every kilometer of expansion. Gas at the top is bound so feebly that radiation pressure on newly formed dust grains can push it away entirely, which is why these stars lose mass continuously, and why their measured sizes, their brightnesses, and their futures are all bound to the same slow shedding of their outer layers. Rarity, applied to stars, is a claim about proportions, and proportions can only be settled by counting, which is why the uncommon kinds of star were not found by anyone staring hard at a single object, but by observers who examined very many objects quickly and kept careful note of the ones that refused to fit. A survey that photographs the spectra of 100,000 stars will produce 99,000 that fall into familiar categories, and the residue is where the interest lies. Almost every unusual stellar class described in the last century and a half emerged from that residue, from plates set aside as anomalous, from a color index that did not match a brightness, from a spectrum that a cataloguer could not assign. In 1867, at the Paris Observatory, Charles Wolfe and Georges Rayet were examining faint stars in the constellation Cygnus with a small visual spectroscope, when they came upon 3 that showed something no other star had shown them. Instead of a continuous band of color crossed by narrow dark lines, these stars gave broad, bright bands standing above the background, wide enough that no laboratory flame of the period produced anything comparable. The observation was published as a short note. The stars were listed, and for some decades afterwards the phenomenon was better described than understood. Interpretation arrived with the physics of moving gas. Those bright bands are emission from material streaming outward from the star at speeds of 1,000 or 2,000 kilometers each second, and they are broad because different parts of the flow move at different velocities along the line of sight, smearing each line into a band. What the spectroscope records in such a case is not a surface at all, but a thick and continuously renewed wind, and the object producing it is a massive star that has lost its hydrogen envelope entirely, exposing layers that were once deep in the interior. Surface temperatures inferred for these stripped cores run from around 30,000 up to well past 100,000 degrees on the Kelvin scale, and the mass carried away in the wind each year, though small in absolute terms, is enough to reshape the star within a geological instant. 3 broad subtypes were eventually distinguished by which element dominates the emission: nitrogen in one group, carbon in another, oxygen in a much smaller third, and the sequence corresponds roughly to how deeply the star has been peeled. Something over 600 such objects have been catalogued across our galaxy, a figure that has grown steadily as infrared searches penetrated the dust of the Milky Way's plane and the total population is thought to be several times larger than the catalogued one. Their scarcity has two causes acting together. Only stars beginning life with something like 20 solar masses or more reach this condition at all, and the condition itself lasts a few 100,000 years, a brief closing passage in a life already short by stellar standards. Among the hot and luminous stars, another small group draws attention by changing. P Cygni, in the northern summer sky, was recorded as a new star of about the third magnitude in 1600. The discovery generally credited to the Dutch cartographer and instrument maker Willem Janszoon Bly, and it then faded, brightened again around the middle of that century, and eventually settled near 5th magnitude, where it has remained. Its spectrum gave astronomy a permanent term, an emission line with a trough of absorption displaced to the blue side, produced when gas expanding towards the observer absorbs light from the star behind it, is still called a P Cygni profile, and it is read as direct evidence of an expanding shell wherever it appears. Eta Carinae, in the southern sky, provided the more violent example. Through the 1830s, it brightened irregularly, and around 1843, it stood briefly as the second brightest star in the night sky before declining over the following decades until it fell below naked eye visibility. No explosion destroyed it. The material thrown off during that episode now forms a small, dense, two-lobed nebula around the star, discovered as a compact object in the 1940s and resolved by later imaging into its bipolar shape, and the mass contained in those lobes is estimated at something over 10 times the mass of the Sun, expelled in a few years by a star that survived the loss. S. Doradus, in the Large Magellanic Cloud, lent its name to the class as a whole, and in the 1950s, Edwin Hubble and Alan Sandage identified a handful of similarly irregular, very luminous blue variables in the Andromeda and Triangulum galaxies, which established that these objects are a recurring stage rather than a local peculiarity. Later work by Roberta Humphreys and Chris Davidson traced an upper boundary in the diagram of luminosity against temperature. Above a certain line, no stable, cool supergiants are found, and the stars that approach it are precisely the ones that erupt. The physical reason lies in the balance between gravity and the outward push of radiation, which, for the most luminous stars, becomes so nearly equal that the outer layers are held only tenuously, and small changes in opacity can lift great quantities of gas away. Angelo Secchi, working in Rome in the 1860s, sorted the stars he examined into a handful of spectral classes, and his fourth class contained a small number of deeply red objects, whose spectra were crossed by broad bands with a sharp edge on one side and a gradual fade on the other. These were later relabeled as classes R and N, then combined into a single class designated C, and they are now understood as stars in which carbon has come to outnumber oxygen in the visible layers. Chemistry accounts for the whole appearance. When gas of stellar composition cools, carbon and oxygen combine first into carbon monoxide, an exceptionally tightly bound molecule, and whichever of the two elements is left over after that pairing governs everything that forms afterwards. In ordinary red giants, oxygen is in excess, giving titanium oxide and water. In carbon stars, the excess runs the other way, producing the diatomic carbon. Cyanogen and hydrocarbon molecules that make Secchi's bands, along with grains of soot that condense in the outflow and redden the light still further. The carbon reaches the surface by convection during the late giant phase, dredged up from the shell where helium burns intermittently, and the dust these stars release into space supplies a large share of the carbon grains found throughout the galaxy. Not every carbon star made its own carbon. A subset of them, including the barium stars and the CH stars, are too small and too faint ever to have dredged anything up, and their enrichment came from outside, transferred across from a companion that passed through its own giant phase and has since contracted into a white dwarf too dim to notice beside the surviving star. Radial velocity monitoring has confirmed the binary nature of many of these systems, and their existence is a reminder that a star's surface composition is not always its own history. Hottest of the ordinary main sequence classes are the O stars, with surface temperatures above 30,000 degrees, emitting most of their light in the ultraviolet and appearing to the eye as a faint blue-white. Their scarcity is severe. Among the main sequence stars in a given volume of the solar neighborhood, fewer than 1 in a million belongs to this class, and yet several are visible without any instrument, including Zeta Puppis, Zeta Ophiuchi, and Alnituk at one end of Orion's belt. That apparent contradiction is a selection effect of the plainest sort, since a star radiating hundreds of thousands of times the sun's light can be picked out from thousands of light years away, while its far more numerous faint neighbors cannot. Edwin Salpeter, in 1955, expressed the underlying distribution as a simple declining relation between mass and number, and every refinement since has preserved its steepness. For each star born with 50 times the sun's mass, many thousands are born with less than the sun's. Short lives compound the effect, because the heaviest stars exhaust themselves in a few million years, while the lightest persist essentially forever. Where the sequence ends has been argued over for decades. Analyses of dense young clusters suggested a ceiling near 150 solar masses, while studies of the brightest members of the cluster at the heart of the Tarantula Nebula have argued for values above that, with the caveat that such masses are inferred from models of the light rather than weighed directly, as only stars in eclipsing pairs can be. Friedrich Bessel spent much of the 1840s measuring the positions of bright stars with more patience than anyone before him, and among his results was an oddity that had nothing to do with distance. Sirius did not move across the sky in a straight line but wove very slightly from side to side, and Procyon did the same. In 1844, he concluded that each must be accompanied by a body too faint to see, whose gravity pulled the visible star first one way and then the other over a cycle of decades. He never saw either companion and died without seeing them. Yet, he had extracted their periods from the wobble alone, and he was untroubled by the objection that nothing was visible there, since invisibility, as he pointed out, is not an argument against existence. Confirmation came in 1862, when Alvan Graham Clark, testing a newly figured lens of 18.5 inches for a telescope bound for Chicago, turned it on Sirius and found a small point of light beside the glare. That companion, called Sirius B, was a puzzle for half a century, because the orbit gave its mass as roughly that of the Sun, while its feeble light suggested something cool and spent. In 1915, Walter Adams, at Mount Wilson, obtained a spectrum of it and found the opposite of what was expected. The little star was white and hot. A hot surface emitting so little total light can only be a small surface, and the arithmetic gave a body no larger than the Earth carrying the mass of a star. Matter packed to that degree, something like a ton in every cubic centimeter, had no place in the physics of the time, and Arthur Eddington was among those who said plainly that the result was absurd and probably true at once. The resolution arrived from the new quantum mechanics. Ralph Fowler showed in 1926 that the electrons in such a body obey the exclusion principle, which forbids any two of them from occupying the same state, so that when the gas is compressed, the electrons are forced into ever faster motion and pushed back. This pressure does not depend on heat at all. A white dwarf therefore needs no fire to hold itself up and can go on cooling indefinitely without collapsing further. Subramanian Chandrasekhar, still in his early 20s, carried the calculation one step further by allowing for the fact that electrons squeezed hard enough approach the speed of light, which softens their resistance. From this he derived a ceiling, above about 1 4/10 times the mass of the Sun. No white dwarf can support itself, and something else must happen. Eddington objected at length, in public, at a meeting of the Royal Astronomical Society in 1935, arguing that nature would surely find a way to avoid such an outcome. The younger man's result survived, became one of the load-bearing numbers of stellar physics, and was cited when he received a share of the Nobel Prize in 1983, nearly half a century after the dispute. What remains, in the ordinary case, is a cinder about the size of a planet, made mostly of carbon and oxygen, wrapped in a thin skin of lighter elements, with no fusion anywhere inside it. Its whole subsequent history is the slow leaking away of heat left over from the core it used to be. The coolest ones known are still several thousand degrees at the surface after many billions of years, since a small radius makes a poor radiator, and the theoretical endpoint, a cold and dark object, has had nowhere near enough time to appear anywhere in the galaxy. Around 97% of the stars in the Milky Way, the Sun included, are expected to finish this way. For heavier stars, the ending was recorded in writing long before it was understood. In the summer of 1054, astronomers at the Song Court set down the appearance of a guest star near the Horn of Taurus, bright enough to be seen in daylight for something over 3 weeks, and still visible at night for roughly 2 years before it faded from sight. Japanese sources describe the same object, and the Chinese records are precise enough about its position and its behavior to be usable as data 9 centuries later. No European chronicle gives a clear account of it, which is one of the reasons the Eastern records have carried so much weight. Charles Messier catalogued a small, ragged patch in Taurus as the first entry in his list of things that were not comets, and a 19th century drawing of its filaments earned it the name of the Crab Nebula. During the 1920s, photographs taken decades apart showed that the nebula was expanding, and running the expansion backwards placed its origin somewhere in the 11th century, at the position given in the old chronicles. Knut Lundmark had already noted the coincidence of position with the guest star, and Edwin Hubble drew the connection more firmly once the expansion rate was in hand. A written observation from 1054 and a cloud of glowing gas measured with a telescope had turned out to be the beginning and the middle of one event. Cassiopeia produced the next well-documented case in November of 1572, when a new point of light appeared that outshone every star and, for a time, rivaled Venus. Tycho Brahe measured its position repeatedly against neighboring stars, and found no shift at all as the night advanced and as the months passed, which meant it lay far beyond the moon, in the region the schools held to be changeless. His short book on the subject made the argument public, and the star faded over about a year and a half, leaving nothing that any instrument of the age could detect. An earlier appearance, in 1006, in the southern constellation of Lupus, was recorded in China, Japan, Egypt, and Europe, and by all accounts was brighter still. Ophiuchus produced the last such event seen with the naked eye inside our galaxy in October of 1604, observed by Johannes Kepler among many others, and described by him in a book published 2 years afterwards. Galileo lectured on it in Padua and used it, as Tycho had used the earlier star, against the doctrine of an unchanging heaven. Since then, the Milky Way has been quiet to the unaided eye, though the expanding shell, now called Cassiopeia A, appears to date from around 1680, with no reliable sighting attached to it, which suggests that dust along the line of sight can hide even a nearby explosion. Walter Baade and Fritz Zwicky, working in California in 1934, gave these events the name supernova and proposed what was left behind. The neutron had been identified only 2 years earlier, and they suggested that in the collapse of a massive star's core, the electrons and protons are driven together, leaving a body composed almost entirely of neutrons, a few tens of kilometers across, with the density of an atomic nucleus. The idea sat in the literature for 3 decades as an interesting possibility that nobody expected to test, since an object that small and that hot would be far too faint to detect at stellar distances. Detection came by an unrelated route. In 1967, at a radio array near Cambridge built to study the flickering of compact sources, Jocelyn Bell noticed a small recurring scruff on the chart paper, which resolved into pulses arriving every 1 1/3 seconds with a regularity that at first suggested a fault in the equipment or a signal of human origin. The team labeled the source LGM1 while they eliminated possibilities, then found 3 more like it in other parts of the sky, which settled the question of an artificial origin, and published in early 1968. Thomas Gold supplied the interpretation within months: a rotating neutron star carrying a strong magnetic field tilted away from its spin axis, sweeping a beam of radio emission past the Earth once per turn like the lamp of a lighthouse. The decisive evidence appeared later that year at the center of the Crab Nebula, where a pulsar was found flashing 33 times a second in exactly the place the collapsed core of the 1054 star should be. Its rate slows measurably from year to year, and the energy lost in that slowing matches the energy needed to keep the surrounding nebula glowing. Age is the most stubborn of a star's properties. Temperature and color can be read directly from the light. A mass can be extracted from the orbit of a companion. Composition emerges from the pattern of absorption lines, but nothing in a spectrum announces how long the star has been shining. Age has to be reconstructed, inferred from where a star sits along a path that no observer will ever watch it travel, and so the search for the galaxy's oldest stars began not with a clock, but with a substitute for one, which turned out to be chemistry. Hydrogen and helium, with a trace of lithium, came out of the early universe. Everything heavier was assembled inside stars and returned to space by winds and explosions, so the gas from which new stars condense grows steadily richer in those heavier elements as generations pass. A star formed late in the sequence carries the accumulated output of all that came before it. A star formed very early carries almost none of it, and keeps that composition in its outer layers for as long as it lives, since the material at the surface never mixes down into the burning core. Enrichment did not proceed at the same rate everywhere, which makes composition a rough ordering rather than a calendar, but the ordering held well enough to point observers toward the right stars. Walter Baade found the first clear division while working at Mount Wilson during the war, when the blackout of Los Angeles left the sky over the mountain darker than it had been in years. Using red-sensitive plates on the 100-inch telescope, he resolved individual stars in the crowded central region of the Andromeda Galaxy and in its two small companions, and noticed that the brightest of them were red giants, quite unlike the hot blue stars that dominate the spiral arms. He proposed two stellar populations, one associated with the disk and its dust and gas, the other with the bulge, the outer halo, and the globular clusters. The second group looked older, and later work showed it was also chemically poorer. Spectra of certain faint stars in the solar neighborhood soon supplied the chemical confirmation. Some of these objects, already known to be moving quickly relative to the Sun, showed metal lines noticeably weaker than those of the Sun, and sat slightly below the ordinary main sequence on a diagram of color against brightness, which earned them the name subdwarfs. Their position had a physical explanation. With fewer heavy elements to absorb radiation in the outer layers, such a star is a little hotter and bluer than a star of the same luminosity and richer composition. Nancy Roman showed that the weakness of the metal lines went together with the excess of ultraviolet light and with the peculiar motions, so that a single family of stars was being picked out three different ways. Astronomers use the word metals loosely to mean everything heavier than helium, and they express the amount as a ratio of iron to hydrogen measured against the Sun on a logarithmic scale. On that scale, 0 means solar, -1 means a tenth of solar, -2 a hundredth. The subdwarfs of the 1950s came in around -1 and -2. Later, surveys pushed far below that, and each step downward meant a step further back toward the beginning of the enrichment process. Motions reinforce the chemical picture. The metal-deficient stars near the Sun do not share the orderly rotation of the disk. They move on long, plunging, eccentric orbits that carry them far above and below the galactic plane, dipping through the solar neighborhood only briefly. In 1962, Olin Egan, Donald Lyndon Bell, and Alan Sandage drew these threads together in a paper, arguing that the correlation between orbital eccentricity and metal weakness recorded the rapid collapse of a protogalactic cloud, with the oldest stars left behind on the orbits they had when they formed. The details have been revised considerably since, as evidence accumulated that much of the halo was assembled from smaller systems swallowed whole. But the central insight survived. The halo is where the galaxy keeps its early record. Globular clusters offered something no individual halo star could. Each is a gravitationally bound sphere of hundreds of thousands of stars, roughly 150 of them catalogued around the Milky Way, and, to a good approximation, the stars in one cluster all formed at the same time from the same gas. That shared origin turns a color magnitude diagram into a measuring instrument. Massive stars exhaust the hydrogen in their cores quickly and move off the main sequence toward the giant branch. Less massive ones remain. As a cluster ages, the point where the main sequence bends away, the turnoff, creeps steadily downward to fainter and cooler stars, and the mass at that turnoff is simply the mass whose core hydrogen supply lasts exactly as long as the cluster has existed. In the oldest clusters, the turnoff has descended to stars of about 8/10 of a solar mass. Converting a turnoff into a number of years demands more than a photograph. The apparent brightness of the turnoff must be turned into a true luminosity, which requires the cluster's distance. The composition must be measured, since metal-poor stars burn differently, and the models of stellar interiors must handle opacity, convection, the settling of helium under gravity, and the initial helium abundance, none of which is known perfectly. Every one of those quantities feeds into the answer, and for several decades, the distances were the weakest link. Because globular clusters lie thousands of light-years away, well beyond the reach of the parallax measurements available at the time. During the early 1990s, the resulting numbers became awkward. Some cluster ages came out at 16 billion years or more, older than the age the universe appeared to have from the measured rate of its expansion, which is not a situation astronomy can tolerate for long. The tension eased from both directions. The Hipparcos satellite provided better parallaxes for nearby subdwarfs, which are used to calibrate cluster distances, and the clusters moved slightly further away and became slightly younger. Independently, the cosmological measurements were revised. Later parallaxes from the Gaia mission tightened the calibration further. Present estimates place the oldest globular clusters somewhere near 12.5 to 13 billion years, with uncertainties of several hundred million years on either side. A second clock sits at the faint end of the same clusters. White dwarfs have no fuel and do nothing but cool, following a rate that theory describes reasonably well. So the faintest white dwarf, a cluster, contains marks how long the earliest of them have been cooling. Deep imaging with the Hubble Space Telescope reached the bottom of that cooling sequence in a nearby globular cluster and returned an age broadly consistent with the turnoff figure, which mattered less for the number itself than for the fact that two independent methods, resting on quite different physics, agreed. Radioactive decay supplies a third approach, applicable to single stars rather than clusters. Thorium-232 has a half-life of about 14 billion years, and uranium-238 about 4.5 billion, and both are made by rapid neutron capture in explosive events. If the amount originally produced can be estimated relative to a stable element made in the same process, the amount surviving in a star's atmosphere gives an elapsed time. The lines are extraordinarily weak and lie in the crowded ultraviolet, so the measurement has been achieved for only a handful of very metal-poor giants, and the ages that come out cluster around 12 to 13 billion years. Surveys designed to sift the halo for the most extreme cases have found stars with iron abundances below 1/10,000th of the Sun's, and a small number below 100,000th. In one southern survey, a star turned up, whose high-resolution spectrum shows no iron line at all, only an upper limit, while carbon and hydrogen remain plainly visible, a composition unlike anything in the disk. Such objects are not necessarily the oldest by direct dating, since their ages cannot be measured individually with any precision, but their chemistry places them very near the start. Not every cluster proves to be as simple as the method assumes. Careful photometry has revealed that most globulars contain more than one population, distinguishable by small differences in helium and in the light elements. And one of the largest, Omega Centauri, shows a spread in iron itself. suggesting it may be the stripped core of a small galaxy rather than a true cluster. The turn-off ages survive these complications, though they now come with a caveat about what exactly is being dated, set beside the 13.8 billion years that measurements of the cosmic microwave background give for the universe as a whole. The oldest halo stars and clusters leave a gap of only a few 100 million years, and much of that gap lies inside the error bars rather than outside them. The material of the galaxy, on this evidence, began turning itself into stars very soon after there was anything to turn. Whatever emerged from the first few minutes of the expanding universe was chemically simple. Hydrogen, about a quarter of the mass as helium, a trace of deuterium and a scattering of lithium, and nothing heavier worth counting. Every carbon atom, every oxygen atom, every trace of iron came later, made inside stars. So the clouds that formed the earliest generation had none of the material that ordinary star formation now depends upon. Cooling matters here more than anything else, because a cloud can only collapse if it can shed the heat of its own compression, and in gas today that heat escapes through the radiation of carbon and oxygen and the dust grains built from them. Primordial gas had only molecular hydrogen, which radiates feebly and which cannot bring a cloud below roughly a couple of hundred Kelvin, and since the mass at which a clump becomes gravitationally unstable rises with temperature, the pieces that broke away from those first clouds were far heavier than the pieces that break away today. Walter Bade, working in the 1940s, had already divided the stars into two populations: the metal-rich younger stars of the galactic disk and the metal-poor, older stars of the halo and the bulge of other galaxies. When theorists later proposed a generation older still, formed from gas that had never been enriched at all, the numbering was extended and the metal-free stars became population 3, so that the sequence of names runs backwards against the sequence of time. Simulations of primordial collapse became possible once computers could follow gas and dark matter together, and the picture that emerged put the first stars inside small concentrations of dark matter of roughly 1 million solar masses, forming when the universe was some tens to a few hundreds of millions of years old. Early calculations, which followed a single clump until it became opaque, produced one very heavy star per halo, perhaps 100 times the mass of the Sunday. Later, work with finer resolution followed the gas further and found the accreting disk around the protostar breaking into pieces, so that several stars formed together, some of them flung out of the system before they could grow. The consensus that survives this refinement is not that every first star was a giant, but that the typical mass was considerably greater than the typical mass now, and that stars of a solar mass or less were rare or absent. Stars of that weight burn quickly and die young, in a few million years at most, radiating mostly in the ultraviolet and ionizing the neutral hydrogen around them out to considerable distances. Their deaths took more than one form. Above roughly 140 and below about 260 times the mass of the Sun, theory predicts an instability in which the core's radiation begins converting itself into electron and positron pairs, the pressure support falters, and the collapse ignites explosive burning that unbinds the entire star and leaves no remnant whatsoever. Such an explosion should scatter a characteristic mixture into the surrounding gas, rich in the elements with even numbers of protons and poor in the odd-numbered ones between them. Stars heavier or lighter than that band collapse instead into black holes, some of which may be the seeds from which the supermassive black holes at galactic centers later grew. If any member of that first generation had been born with less than about 8/10 of a solar mass, it would still be shining now, and it would be recognizable by a spectrum showing hydrogen and helium and nothing else. Searches for such an object have been going on for decades, first with objective prism surveys that could sift thousands of halo stars for weak metal lines, and then with dedicated spectroscopic follow-up on large telescopes. The searches have found stars of astonishing chemical poverty, with iron abundances below 1 part in 100,000 of the suns, and a handful lower still, including one in which no iron line could be detected at all, and only an upper limit could be set. Yet every one of them carries something: carbon, usually in quantity, or magnesium, or calcium. Not a single truly pristine star has turned up in any survey, and that absence is itself a measurement, since it supports the theoretical expectation that the first generation formed few or no low-mass members. A complication attends this conclusion, because a star that began without metals need not stay that way for 13 billion years. Passing through interstellar clouds, it would sweep up gas and dust onto its surface, and in a star with a thin outer convective layer, that material would remain near the top rather than being mixed away, so the spectrum would show a contamination that has nothing to do with the star's birth. How much accretion actually occurs, and whether radiation pressure or the star's own magnetic field keeps the dust out, remains unsettled, which means the failure to find a metal-free star is suggestive rather than conclusive. Direct observation of the era has become possible only recently, and only in the infrared, since light emitted when the universe was young arrives stretched by the expansion into wavelengths the atmosphere largely blocks. The James Webb Space Telescope, placed beyond the Moon's orbit at the end of 2021, and built with a mirror cooled to work in that part of the spectrum, has identified galaxies whose light set out within a few 100 million years of the beginning. Individual stars at such distances lie far below the reach of any instrument, except where a massive foreground cluster of galaxies happens to bend and concentrate their light, and a few single stars in remote galaxies have been picked out this way. What would settle the matter is a spectrum showing strong hydrogen and helium emission with no metal lines at all, and that has not yet been found. At the opposite end of the mass scale from those first stars lie the ones that will still be burning when everything else has gone out. Red dwarfs, the stars of spectral class M, run from about 8% of the Sun's mass, below which hydrogen fusion never starts, up to roughly half of it, with surfaces near 3000 Kelvin and luminosities that can fall below 1,000th of the Sun's. They are the commonest stars by a wide margin, making up roughly 3 out of every 4 in the volume around the Sun, and not one of them can be seen without a telescope, including the nearest star to the Sun, which lies just over 4 light-years away and shines at about the 11th magnitude. 2 effects combine to stretch their lives. Luminosity climbs very steeply with mass, so a star of 1/10 of a solar mass has 1/10 of the fuel, but consumes it thousands of times more slowly, and below about 1/3 of a solar mass, the interior is convective throughout, circulating the whole star rather than only its center. The Sun will exhaust the hydrogen in its core while leaving 9/10 of its hydrogen untouched in the layers above, whereas a fully convective dwarf can eventually feed almost all of its hydrogen into the reaction. Calculated lifetimes run to hundreds of billions of years for the heavier red dwarfs and to trillions for the smallest. Because even the shortest of those spans exceeds the present age of the universe by a factor of many, every red dwarf that has ever formed is still on the main sequence, still fusing hydrogen, still in its youth by its own reckoning. Nothing has been observed at the end of such a life, and nothing can be. So the later chapters of their evolution exist only as computation, run far beyond the point where any observation could check the result. Models carried forward in that way suggest the smallest of them will never become red giants at all. As helium accumulates and the mean molecular weight rises, the star slowly contracts, growing hotter and bluer over hundreds of billions of years, passing through colors no star has ever displayed, before the hydrogen runs low and it settles into a white dwarf made of helium, cooling in the dark for ages afterwards. Star formation across the galaxy has been declining for billions of years as the available gas is consumed, locked into remnants, or driven out, and the trend points toward a time when the bright, heavy, short-lived stars stop being replaced. What will remain in the sky afterwards is what was always most numerous and least conspicuous: the faint red stars that waste nothing and are in no hurry, holding the last light of a galaxy whose brilliant interval, the one in which all the constellations were named, will by then be long over. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.